How's the semester going? Is it chill this time of year, or is it busy right now?
This is time for civic year.
Oh, that's a fair point. True story. Cool. Let's get started. Today is very exciting. So, brief recap. We're still in the module neural networks as prior-based inference algorithms. So, what does it mean? Reminder, project proposal due November 9th. I encourage you to come by my project office hour. Oh, sorry, just my office hour, and discuss your project with me if you want to. Cool. So, brief recap. The past two lectures, we were talking about this general framework for autoencoding based on scene representations. So we said we take images as input, we have some kind of inference network, which is kind of like a convolutional encoder or something, then we produce a set of latent codes, and then we can use these set of latent codes to condition a 3D scene representation on them, or reconstruct a 3D scene from these latent codes, and then we can render that using our differential renderer. Any questions on that? Excellent. We briefly talked about like auto decoding, and we talked about auto encoding. I'm not going to repeat that again. We also, and this is what we spent most of the last lecture on, talked about local conditioning, and how is it that if we build our encoders and our latent codes carefully, and the way we reconstruct the scene representation from our latent codes, that we can generalize to out-of-distribution scenes, where the out-of-distribution aspect was that we were talking about compositional scenes, so scenes that are composed of several objects, even though you have only seen single objects at training time and so on. And if you remember correctly, the key property that allowed us to do this was this notion of end-to-end locality, or end-to-end shift equivariance. And we were comparing that to fully convolutional neural networks in 2D, just in the same way we can basically build fully convolutional 3D models, and we can keep the same kinds of properties. So today we're going to talk about some more hacky stuff, or not hacky, but like less well understood stuff. So we're going to talk about transformers and how transformers fit in here, because of course transformers fit in here, but in an interesting way, not in a weird black box way. How does this, actually we're not going to talk about that. And we're going to talk about light fields. Cool. Let's dive right in. So we're going to, in fact, start with light fields. So if you might remember, some few lectures ago, I think when we were talking about differential rendering, I had asked you about a neural network that looked a scene representation that looked slightly differently. So as a recap, right, if we build 3D scene representations, then usually our renders look something like this. We shoot a ray, then we sample lots of points along the way, for instance, from our voxel grid or from our neural field, like our nerf, and we have like a volume renderer that allows us to render it, right? And the downsides of this, as we had already discussed, is that it's like very expensive. You need to take like hundreds of samples per ray, and it's very time and memory intensive. Okay, so here is a slightly, oh wait, not again. Here's a slightly different thing. What if, instead of taking 3D points along the way as input, you build a neural network that, or like you imagine you build a neural field, so a neural network that doesn't take as input a 3D coordinate and then gives you the density and the color for that 3D coordinate, but instead it takes a 3D ray as input, which imagine a 3D ray, for instance, is a point and a direction, right? And then instead of giving you anything else, it just directly gives you the color of that ray. Does that make sense? So what do you think would happen if you did that? So like, let's say I think I asked you this before. So just to be clear, right, what that means then is that the neural field in this case wouldn't take as input a 3D coordinate. It would now take as input 6 coordinates, like three coordinates of a point, and then maybe a direction, like a normalized direction. And then it'll just immediately give you the color for that ray. And just for a brief moment, let's think about if that is like a valid scene parameterization, right? It's kind of not obvious. I think I actually skipped the slides. Maybe I should have kept them in there. But we talked about this, in fact, before. This is what is called a light field, and was actually formalized here at MIT by a guy called Ted Adelson. He's still here. And the idea here is, right, that you would just, in this room, for instance, represent the color for every possible ray in this room. And with a lot of thinking, you can convince yourself that that has, in fact, the same amount of information than a nerf of this room, for instance. Like if you have if you can store the color for every possible ray in the room, it's kind of the same as it's the same information content as if you store the 3D scene, like the 3D geometry and the 3D appearance of the scene. Okay, so what happens if we try to, and we talked about this before, what happens if we try to fit this in like an overfitting framework? So let's say we built this neural network like a nerf, right? And then we just take a set of images of some scene. Let's say, for instance, we take a set of images of this fern, but you can also imagine that you take a set of images of the room that you're in, right? And now we just fit our scene representation to this set of observations. And just to be clear, how can you do that, right? Of course, we already know the equation that gives you for a given pixel and for a given camera pulse, the ray for that pixel, right? So that's no magic there. So it's just for each of these pixels, you would just get the corresponding ray, and then you would just give that ray to the neural network, and you would supervise it with the color of that pixel. Does that make sense? Okay, cool. What do you expect to happen? I mean, it's kind of a giveaway on the right-hand side. If you then try to render novel views, so now you now move the camera to a point to a perspective that wasn't in the training set, what would you expect to happen?
I mean, I think it kind of said it already, but you're not forcing it to kind of share any information with, like, among different views. So there's nothing encouraging it to give you a meaningful output for any view that's not in your.
Did everybody hear this? So what happens, right, is this network doesn't have any 3D structure. So what happens in practice is that there's nothing in here that enforces that this network basically shares information across these rays. And it's actually a very powerful thing to think about what sharing information in this context means. So sometimes we say that so in a way, the way you can think about a 3D scene is kind of a very compressed representation of all possible videos that you can capture in that 3D scene, right? Imagine there's a static 3D scene, like nothing moves. There's just the 3D scene and nothing moves in the 3D scene. And now imagine a camera moving through that 3D scene, right? The images that the camera is capturing can all be explained via the 3D scene and the camera pulse, right? So it's actually much like, in a way, you can think about all of the structure that we're building allows us to store all possible videos that you can capture of a 3D scene in a very compressed format, which is that 3D scene representation. However, now, if we just do this, there's nothing that forces this network to compress this information or discover any meaningful structure, as you say, in this data. So actually what happens is if you try to render novel views of this thing, and it kind of depends on what architecture you pick for the network, it might look different. This is with positional encoding, or like with the siren. This is what you might get with a siren or something. And it's just complete noise. It's complete garbage. Because the moment you move, and you know a lot about this kind of stuff by now. You can, for instance, think about this in terms of this neural tangent kernel shenanigans that we were talking about, right? What this network basically does is if you sample it with a new ray, it'll have learned some kind of kernel that it uses to figure out the color for that ray. So it'll interpolate the colors that it has seen at training time. And there is a correct kernel. There's a correct way of interpolating the colors, which is basically figuring out which rays hit the same 3D point and then using that information to figure out the color. But of course, the network won't do that. It will do some weird nearest neighbor thing to pick these colors, and it'll just be complete garbage. Okay, so that doesn't work. However, we have learned a few things by now. One of them is that we don't need to do this overfitting thing. We can, of course, also condition our neural network, or basically treat our neural network in this generalization case. So instead of just reconstructing a single scene, we can learn a prior over all possible 3D scenes, right? And then using this prior over all possible 3D scenes, we can reconstruct a scene from a single image, right? So now here's something to think about for a moment. So the problem that you just discovered one moment ago, where did this problem come from? One way to think about this problem is that, think about it like this. There is a set of, think about this class of functions that maps rays to colors, right? So this space of functions is huge. There's an infinite number of possible functions that map rays to colors, and only a tiny subset of them are functions that correspond to real 3D scenes, right? There's some subset of these functions that correspond to real 3D scenes. Does that make sense? that are kind of multi-view consistent when you render them. And now one thing you can think about with all of the tools that we have discussed so far, you can think that maybe a reasonable thing to do is we say we learn a prior not only over the 3D scenes, but we also learn a prior that says among all of these possible functions, I always want you to find a function that is 3D consistent. So by using the same kind of stuff that we built for generalizing across scenes, it turns out we can also learn functions that are multi-view consistent. Let me give you an example. So this was a paper that I wrote in my postdoc. So this is from 2021. The idea is very simple. By now you'll understand it. So what we're going to do is it's going to look exactly like this. But now instead of using our latent code to decode it into a voxel grid and then render it via differential rendering or decoding it into a neural field or something like that, we're just going to take this latent code and we're just going to use it to condition a neural field that takes these rays as inputs. So exactly the same as before, just now this neural network doesn't take points as input, but now it takes rays as inputs. So basically, like exactly what you saw here, right? So we have this neural field, and now this neural field takes a latent code Z as input. So this latent code could be obtained via auto-decoding, as we had discussed before, or it could be the output of a convolutional encoder or anything like that, right? And now this neural network is just a neural network that takes, instead of three coordinates as input, it just takes 6 coordinates as input, and these build these rays. And now you can do the same exact thing again, right? You can train it on your data set of like little toy cars, for instance, and that should just work, right? There's no problem with this. So let's see what happens if we do that. So this is, in fact, this exact model that we just discussed, trained on the ShapeNet cars data set. And as you can see, it looks pretty reasonable. So this is cars that are reconstructed from a single image. So this is a light field. So this is now exactly a neural network that is queried with rays instead of being queried with 3D coordinates along rays. And as you can see, it works pretty well. So why would you ever want to do this? One reason why you might want to do this is because this is really cheap, right? Like now this network, if you want to render a ray, instead of having to query it 1,000 times for every point along the ray, you all have an appreciation if you started with the homework how incredibly slow this is. Instead of doing that, now you can just query your network a single time, and it'll give you a color, and you're done with rendering. Versus on the right-hand side, just for dramatic exposure, you can see the pixel nerf reconstructions of these cars. So this is done with pixel nerf, and of course pixel nerf renders with 196 evaluations per ray, and it renders with 0.033 frames per second. So that is significantly slower, right? Makes sense. Okay. You can also encode these like simple 3D scenes, like these ones here. So these are like little room scale scenes, but it's not clearly like, okay, so you can do this. So this is all done via, this is in fact done with auto decoding. So by now you should probably, you should know how this works. Okay, so here's like actually a little table from the paper. So on the top row, that is scene representation network. So this is the little thing that this little paper that I wrote a long time ago with single objects done via 3D differentiable rendering. So this is just what we had discussed before, this auto decoding framework single. And as you can see, it's basically the same. So performance is exactly the same, except that now we don't do 3D structured differential rendering. We sample the neural network with a ray at a time. Okay, but it does not outperform pixel nerf. So in other words, like the model that we talked about last time with local conditioning, it does not outperform that. And by now, maybe you have an idea, like what could be the problem with this network that we, judging from the last lecture, what is the problem with this architecture? So we discussed limitations of using a single latent code for reconstructing, for parameterizing 3D scenes, right? Do you remember what that limitation was? Yes? Okay, both of you, yeah. Yeah, go ahead. Exactly. So the problem is exactly the same problem as we had discussed before, which is this problem of out-of-distribution generalization. So, and this shows up dramatically, as we'll see in a moment again. This shows up dramatically with scenes that are composed of several different things, but actually even for these little toy cars, it shows up. So even if you try to reconstruct a data set like this shows up. Just to give you an idea, imagine you see a car which has like a spoiler that you have never seen before, or this has some element that you've never seen before. Your pixel-nerf model or your locally conditioned model will have a much easier time making a reasonable estimate at that, just by virtue of being a shift equivariant, right? So maybe, for instance, it has seen, maybe in the training set there were 2 different cars, maybe one Humvee and one sports car, and the sports car had a spoiler, but the Humvee never had a spoiler. So this model with global conditioning will never be able at test time to reconstruct a Humvee with a spoiler. But for the local conditioning thing, it's fine. It'll be like, this is a spoiler. I know approximately where it is. It'll reconstruct. It'll be fine. So even for these little toy cars, it turns out that if you reconstruct these little toy cars, it'll be better with local conditioning. So pixel-nerf, just for the record again, pixel-nerf was this model that did like encoded an image with a convolutional neural network and then did this projection shenanigans. Does anyone not remember how pixel-nerf worked? Does everybody remember how pixel-nerf worked? Yeah? Okay, good. Please ask questions if you, I'm realizing now as I'm talking that there's like lots of words that I'm just taking from previous lectures, but I'm not sure if I had highlighted them enough. So if you're missing some context, please just say it and we'll explain it. Okay, so global conditioning is like a problem because it can't generalize to compositional scenes, and it actually just fails to generalize often. But there's another problem here. So like since this is the problem, right, like what would be the natural fix? Ideally we want to build a light field network that would be locally conditioned, right? So like pixel-nerf. Remember how did we fix this with 3D scenes? We basically did this trick where we connected 3D coordinates to pixel coordinates via projection. So if you wanted to decode a 3D coordinate, we projected it onto the image plane. We got the feature from the convolutional encoder there, and that's what we decoded to get our nerf, right? So ideally, we would now do the same thing with our light field networks. So let's try to do that, or let's think about this. The problem here is that our light field, our rays, there is no straightforward local relationship between rays and image planes. Or maybe you can think of some. So what is a set of, what is the relation? If I give you a ray in space, do you know of any way of how you can connect pixel coordinates to rays in space, 3D rays in space? Yes? Right, so that was the point of an epipolar line, right? If I have a ray in 3D, then the set of all pixels that, if you have a ray in 3D, then it projects onto an image plane as an epipolar line. So that is one way of doing that. And in fact, that can be done, but we're not going to discuss it right now. But long story short, it turns out that this is kind of, if you wanted to use a version of local conditioning for these light fields, it gets a little bit tricky. It's not as straightforward. 3D points in space, they project to 2D points in pixel space. That's easy. But now you have rays, they project to epipolar lines, it gets a little bit tricky. So is there another way of conditioning these neural scene representations that could maybe help us fix our problem? And the answer is yes. And this is now the motivation for transformer-based conditioning, or for transformers. So I hope that all of you kind of know what transformers are or how they work. We're going to have a brief discussion today of these 2 different other kinds of ways of reconstructing 3D scenes or parameterizing 3D scenes. We talked about global conditioning, local conditioning. Now we're going to talk about transformers. Who does not know how a transformer works by now? Okay, good. Brief refresher, right? So transformers are built about this idea of attention. And I'm going to refresh it because we're going to in a moment discuss transformers from a perspective that is a little bit different than how these are usually discussed. So I'm going to refresh your memory on this. So the idea of softmax attention kind of looks like this, right? You have a set of values, like for instance the patches in an image, or you have tokens in a sequence, right? And now you run this operation on them, which is called self-attention. Self-attention is basically the engine behind transformers. How does self-attention work? You would take your set of tokens, let's say you have n tokens, and for each of these n tokens you would predict a query, a key, and a value, which are each vectors, right? And now you would stick all of these into the softmax attention. So what does that mean? You take one token, you get its query, and now you take the dot product of this query with the keys of all the other tokens, right? So this is the dot product here. So this is the query token. You take the keys of all of the other tokens. That gives you a scalar for each other token. And now you normalize these with the softmax, which basically gives you a normalized probability distribution over all of the tokens in the sequence. And intuitively, the way people usually explain this is by saying, okay, so basically the query token is asking which of these other tokens is most relevant to me, right? And then you basically get a weight for each of the tokens in the sequence. So this gives you a weight for each of the tokens in the sequence, and now you have the values for each token, and you do a weighted sum of these values according to these weights, right? So this shouldn't be new. And then you get a new value for that token that you use to compute the query, and that's the new value, give or take a little bit. Does that resonate with everyone? This is obviously only a tiny part of it, but just okay, good. Cool. So this is the engine, for instance, behind vision transformers. So you have probably seen something like this before, but this is just a vision transformer. We actually mentioned this before. You take an image, you split it into patches, and now you treat each of these patches as one of these tokens. So now this is this set of tokens. And now usually you, well, actually, let's skip this. Let's just say these are tokens, right? And now you would just stick these exactly into this self-attention layer. So like the self-attention would now take these as input and query key value, right? And then recompute a new value for this token as a weighted sum of all the tokens in the sequence, right? So this is the idea of self-attention. And then you have like several heads and you stack this a bunch of times, but that's the idea of a transformer, right? Okay, have you learned about this before, or do you know, does that make sense? Yes, good, okay, great, excellent. Cool. Now, here's a perspective on transformers that you might have not heard before, or like a perspective on attention that you might have not appreciated before. So, remember when we were talking about interpolation of grids? Like imagine, right, I give you a 3D voxel grid, and the 3D voxel grid represents, for instance, this room, and in each voxel you store a value. We were discussing this idea of interpolation in that grid, right? I told you, like, okay, if you now want to query a 3D coordinate in that grid, if that 3D coordinate doesn't happen to fall exactly onto the center of a voxel, you have to do this thing which is called interpolation, right? Like trilinear interpolation, which means you express this the value at this point as a weighted sum of like a local neighborhood. In trilinear, it would be like the local neighborhood, like eight points in like, or cubic or whatnot, right? Okay, good. And now we discussed that you can use this kind of as a way of conditioning our 3D scene representation, right? We could say, okay, let's say we represent this room as a coarse voxel grid. Each voxel stores a feature. And now we can parameterize the nerf in this room by saying, okay, for a 3D coordinate, we do trilinear interpolation for the features. We get a feature for that coordinate, and then we stick it into a neural network, right? And then that neural network is going to output the density and the color, right? Does that still make sense? Okay, good. So now, consider this. Consider that one way to look at attention is just as a way of learning how to interpolate a set of points. Okay, so what that means is, imagine you now have an x coordinate, like you have this 3D coordinate x. And now, of course, what you can do is you can say, okay, let's say I have a set of tokens, and I say the set of tokens represents my 3D scene, right? And it's actually the same as the voxel grid. In the voxel grid, right, you also had a set of tokens, which was just the values in every voxel, right? Now you are kind of throwing away this local idea, and you're just saying I'm representing my scene as just an unordered set of tokens, right? And now it's perfectly reasonable to say the following. We're going to take a 3D coordinate x. We're going to encode that 3D coordinate x into like a high-dimensional vector. Could be via just a linear layer, right? Takes 3D as input, gives you n dimensions, or you could do positional encoding, doesn't really matter. You just take x, encode it into a high-dimensional vector. And now you use the idea of cross-attention or dot product attention to interpolate your set of tokens that represent your 3D scene, right? So now you have a set of n tokens. You take your 3D coordinate x, you embed it, you do a dot product with the key values that you predicted from each of your tokens. That gives you a weight for each of your tokens via the softmax. And now you just do a weighted sum of the values of these tokens, and that gives you value. Okay. And the way I want you to think about this is really exactly as a way of doing kind of interpolation. It's kind of learning the kernel, right? In the case above, we kind of, in the case of a grid and bilinear interpolation or trilinear interpolation, we hard-coded the kernel that interpolates the values in the grid. And now we're learning the kernel. We're basically saying, okay, we know what we want to do is we want to express the value at the 3D coordinate as a weighted sum of tokens, but we don't know how we should weight them. We don't know like the function that we should use. Maybe, for instance, you don't know the idea of like, it's very hard to encode the rules of locality, maybe, for instance. Okay, and then once you have done that, once you have produced a weighted sum of your values, you can just, again, stick that into a neural network. And for instance, you can use that to predict a color and a density, right, at that 3D coordinate. So you can use this to parameterize a nerve. And in fact, there is a bunch of papers that do exactly this. I don't have them in the slides, but this is something that people have done. Okay. Good. Does that make sense? Yes?
So, like in a transform, I would expect like you have a box will create it, and every box will have its own token.
Yeah, so I'm realizing I'm not doing a very good job at explaining this. So right now, we haven't talked yet about how to get the tokens. So right now, we are just talking about imagine you have a radiance field. You have some function you want to parameterize, like the function that takes a 3D coordinate as input and outputs a density and a color. And now imagine we're in this overfitting domain where you really just, you have a lot of images, for instance, and you're just trying to figure out the values, like you're just trying to learn that function, right? And this is kind of the domain that we're talking about right now. So imagine you just, the comparison that I'm drawing here is imagine you're parameterizing your scene as a voxel grid. And then you can just like render lots of images, and you're just figuring out what values to put into your voxel grid via optimization. And the bottom case is now kind of the equivalent of that. Your scene is, you just pick a number of tokens. You say, okay, I'm parameterizing my scene via 1,000 tokens, and they're just an unordered set. And now the way I'm going to fit my function is I'm just going to always like render array just like in your nerve, right? You sample points along the array, and for each of these points, you'll now do this thing to get the density and the color, and then you're just backpropagating directly into these tokens to get the values for the tokens. Does that make sense? Good question. Does that make sense for everyone? Yes? That's a good way to think about it. So yeah, so if you have only been confronted with transformers in the framework of natural language, which is honestly quite reasonable, which is the frame where most people are confronted with them. Although in vision, they're also omnipresent. Like vision transformers are the so this is indeed a good way to think about it. So like enough said. Actually, yeah, this is a good way to think about it. You're saying like the value of this new token is a weighted sum of the past words, like is a weighted sum of the tokens of past words, right? And now you're saying the value for this new token is a weighted sum of like spatial tokens. And you don't exactly know, like one way to think about this is for a moment think that, okay, you're representing your scene as 1,000 tokens, right? Imagine that each of these tokens could be parameterizing some region of 3D space. Imagine there's like tokens floating in space, right? You haven't actually put them there, and it's like, it's hard to think about that, but like imagine there's just tokens floating in space, and now I ask you the value for this 3D coordinate, and now you'll just, in this kind of weird way, you're just going to ask each of the tokens, what's your contribution to this 3D coordinate? And then you're expressing the 3D coordinate as a weighted sum of these tokens. Make sense? Yes? Right, and now comes the tricky part, which is that this is the tricky part and the magical part about transformers, and I think you'll find that this is going to be the topic of much research over the next few years. The tricky part is that this notion of near is not something that you're defining. It's something that the transformers figures out by itself. Because the transformer figures out by itself, like what is the criterion by which I want to take a 3D coordinate and like relate it to all of the tokens that represent my 3D scene, that is something the transformer learns by itself. So, but yes, intuitively, what you might expect is that maybe each of the tokens will learn to like take care of some piece of space, although that is not at this point published or universally understood. Okay, but we're building up to something, which is the following. Okay, so we can, what is this? So here we can now basically use this idea to build a light field network. So this is work from Google from 2021. It's called the scene representation transformer. And let me briefly tell you how this model works. This model takes a set of images as input. Imagine you have a set of images of this 3D scene here. So like, I don't know, 1, 2, 3 or something, right? 3 images as input. And now what it's going to do is in the first stage, it's going to compute a set of tokens that represent this scene from the set of images. Okay, and how is it going to do that with a transformer? So it's going to take these images, like input image 1, input image n, right? It takes n images as input. And now it's going to do this VIT thing. It's going to split each of these images into tokens. And now it's just going to hit it with the transformer. So it's just going to do self-attention, 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 self-attention across all of these patches, right? Unfortunately, there's nothing to understand here. But like, can you imagine you just build a big transformer? It takes like these sequences input. Just the sequences now aren't words. The sequences now are patches of images. And it's not just patches from a single image. It's patches from several images, right? Does that make sense? So, okay, build this big vision transformer. And you just throw in all the patches. You're like, whatever. I don't know what's going on. I'm just going to put in all the patches. And in addition to each of the patches, imagine you also know the pose. What we're going to do is we're going to hand wave this again. You know the idea of positional encoding in transformers, which is basically the idea that for sequence models, you usually do this thing where for each token in the sequence, you don't only give the transformer the vector of that token. You also give it the positional encoding that encodes the position in the sentence, right, relative to the token that you're trying to generate. Here we're going to do something similar. For each token, we're also going to tell the transformer this is the pose of the camera, and this is the position of this token in the image. So like, imagine each token has a 2D pixel coordinate and it has a camera pose attached to it, and you're just going to black box throw that in there as well. Imagine you just concatenate it with the token, right? You're just like, okay, whatever. I'm just concatenating everything to these tokens, and I'm just going to throw it in my transformer, and then it's going to just turn the self-attention crank. Does that make sense? Good. So we do that a bunch of times. Okay, so, well, first the CNN doesn't matter. So this is what this part does, right? So it basically takes these patch embeddings, and then it just does, like, self-attention a bunch of times. So self-attention, like, what do they? 10 times self-attention. 10 layers of self-attention. We don't know what's going on. Okay, and out pops the set of tokens. This is now the set of tokens that we were just talking about. This is now the set of tokens where we say this set of tokens now magically represents our 3D scene. We just assume that the transformer will take all of these input tokens. Now it's going to turn the crank, and it's going to say, okay, from these input tokens, I can now produce this set of tokens which parameterize my 3D scene. So in other words, right, we take these images as input, split them into patches, and now we say, okay, the transformer now just like magically figures out which parts of, how to use these tokens to best represent my 3D scene. And now comes this magical thing that we just discussed. Now we want to render array. How are we going to render that array? We're going to take our array, which is just a position and a direction. We're going to positionally encode it, and then we're going to do cross-attention, which is exactly the thing that we were just discussing. We're going to take this token, and we're going to just do attention over the tokens that are the output of our encoder, right? So we just do, and we do that twice. We do like 2 rounds of this attention over these tokens, and out pops the color. Does that make sense? Or like, let me ask differently. This doesn't make sense per se, but can you mechanistically appreciate what's going on? Like, which is basically, we built this big black box, takes images as input, produces a set of tokens, and then we're going to do cross attention. Okay, good. So now, what is interesting about this? What's interesting about this is this works. Let me give an idea. So you might not be that impressed yet. But we're going to get there. And so this is just ShapeNet. So this is all these toy cars that we discussed before. This is the input image. It's supposed to be low resolution. This is the input image. This is the rendering of light field networks, which is the thing that we just discussed before, which was basically we parameterized the scene via a global latent code, and we had our null field parameterize the light field. And now this is pixelnerf, right? So pixelnerf you also already know, right? Which was the locally conditioned version. And now this is the scene representation transformer. So this is the thing that just takes array, like this is the thing that we were just discussing. So what this does, in this case, where it just takes a single image as input, takes the single image, splits it into tokens, does self-attention, gets a set of tokens out, and now it renders array by taking array, doing cross-attention over these tokens, presents a color. Make sense? Okay, good. How does that express itself in numbers? This is light field network, so just the model with globally conditioned null field. 25. This is on ShapeNet. This is on these little toy cars. PSNR of 25 dB. Pixelnerf, which we already know, 27 dB. So this is the gap that we were just discussing about. So this is local conditioning versus global conditioning, basically. And this is the scene representation transformer. So this is 28 dB. Okay, so significantly better. But maybe you're like, okay, who cares about little toy cars? Fair point. Let's make it a little bit more complicated. Here's a set of synthetic still, but synthetic, I don't know how to call this, trash heaps of objects. You basically take, this data set is generated synthetically. You just take, like, imagine like Unreal Engine, you just make you pick some random background and you just drop 50 objects on the background and you're like done. So this is my scene now. And then you render a set of input images. So now it's 5 images, right? 1, 2, 3, 4, 5. You give that to your transformer, hit it with a transformer stick. And now here are the renderings that you, so this is now what Light Field Networks does. This is global conditioning, and you can see this is garbage, right? And you know why this is garbage? Because global conditioning, compositional, la-di-da, all the things we were discussing before gives you complete garbage. Unsurprising. This is what pixelnerf gives you. And you can see pixelnerf gets it, like sometimes it gets it almost right? If you look at this image here, this is the target image, so this is ground truth. So pixelnerf clearly figures out that like this object goes there, kind of gets the geometry approximately right. So you can appreciate one more time the point about local conditioning, compositional scenes, la-di-da, right? But now look at the scene representation transformer. This is what the SRT gives you. And you can appreciate that it's blurry, but the SRT actually does really well as well. And it works pretty well. And in fact, if you look at the numbers, the scene representation transformer is about 1 dB better in PSNR than pixelnerf. So the SRT actually outperforms this locally conditioned pixelnerf thing that we were just discussing. And now, why is this? Okay, so like, what does this look like in images? Because an image speaks more than 1,000 words. So this is something that unfortunately only Google can do because only they have this data set. This is a data set from Street View. This is the Street View data set, which is not public. They went ahead and they trained this model that we were just discussing on Street View, which takes like I think between 3 and 5 images as input, and then they train it in exactly the same way that we were just discussing. Images input, render, transformer, la-di-da. And these are novel views from the data set. Okay, so you might look at these images and you're like, this looks trash. This is hella blurry. We've already seen results that look better than this. But, and it's true, last time actually we did talk about a paper that looked better than this, but it had a bunch of stuff going on with like epipolar lines and so on. This has nothing going on. Like no one spent a single hour on like designing any kind of local geometry, nothing for this thing. They just like hit it with a stick and they're like, nice, works. It's great. Nothing, I'm not trying to minimize the contribution. This is a cool paper and I encourage you to read it. Although now you kind of know how it works. That's all there is to it. So conditioned on that, it's actually extremely impressive, right? So like, let's think about all of the things that this thing figured out, right? It figured out, for instance, clearly it figured out the notion of 3D geometry. It's like, if you look at the what is this called? Like the lamppost, right? Clearly the lamppost is rendered multi-view consistently. There's no question about it. Like you're rendering these views, looks totally fine. The cars are clearly rendered correctly, right? This is like an underground thing. There's some artifacts, some blurring going on, but like works perfectly fine. These are scenes that are reconstructed from like 3 images at test time, right? So this is honestly quite impressive. Okay, so now I wish I could kind of give you a big solution on like what's happening here, or like why is this happening and why does it work so well? But the truth is that we don't really know. We just literally don't know what's going on. So you could, this is one of the most interesting things in this area of research right now, and this is very related to other things that you might see in natural language processing, where one way, I think, to productively think about this is that, there's good news and there's bad news. So what's the bad news? In natural language processing, some people are like, oh, great, natural language processing finally works. Surely all of the researchers that work on natural language processing are super happy because it now works. But have you ever talked to a researcher that does natural language processing? Many of them are very sad. Not all of them, but many of them are very sad. Can anyone appreciate why they're sad? Well, think about it this way. This happens to all the fields from time to time. It'll happen to vision. I mean, arguably, it's happening right now to vision. Right? Here's a field that for 50 years, they have built all this nice theory about how language is supposed to work. You build these parsing trees. You think about grammars. You think about syntax. You think about all this cool, fancy stuff. And you try to build neural networks that kind of exploit all of this. And you're like, yeah, this is going to be great. But nothing actually ever works. These things didn't work. None of the stuff we built until 10 years ago did anything whatsoever, right? Basically. And then suddenly, someone comes across and they're like, forget about it. We're just going to hit it with a big stick. And we just built these transformers, and we're just going to train it on all the data. And we just shovel it in. We have no idea what the fuck is going on. But that's fine. It's totally fine because it works, right? And that's exactly literally what happened. And so from one perspective, this is, of course, great, because now stuff works, kind of. But it's also sad, because we don't understand what's going on. And all of this fancy theory that we've built helps us nil to understand what's going on in these transformers so far. I think they'll be I'm not trying to overstate this case. There will be a reckoning to some degree. There's no magic in any of this, right? Just as with neural networks before, 7 years ago, we figured out how neural networks kind of worked. We will figure out how transformers work, and we will understand better what's going on. But status today, we have no idea, or we have very little idea. And so now the same is true for vision transformers. But I think I can indulge you a little bit in what might be going on, right? So this is the bad news. The bad news is we have no idea what's going on. And so as a consequence, you might get sad and be like, okay, why did we learn all this stuff? The good news is that vision is different from natural language. In natural language, we literally don't understand what the geometry of language is. We literally don't understand it. But in vision, all of the stuff that's going on right there, you can write down exactly what is going on. You can say exactly what the color of this ray is, conditioned on the input images. Because you know it. That's what we talked about all the time. We derived it. This is multi-view geometry. We know exactly how inference should work. We know exactly what does this thing have to do in order to render these views? Well, it has to figure out the depth of 3D points. We know that much. At some point in this scene representation transformer, it has to do inference about the correct 3D location for each of these pixels. There's no way around that. Otherwise, it wouldn't show you these renderings. So all of these things that we know will, in the coming months and years, help us taking this thing apart and understanding what's going on, and hopefully that will inform us building better things. And that's the good news. So the good news is vision is different than language. We know the geometry, so this will help us reverse engineer what's going on. Yes?
Have people tried to extract embedding from the interior stages and convert
Yes, there's some of that being attempted, and you can get some insights. So in fact, I don't have these slides in my presentation right now, but so maybe you can, let's think about this a little bit. So if I asked you to try to figure out what is going on, Cairo, you can't say anything because Cairo was working with this thing. So if I asked you to take this model this model is trained, and I asked you to figure out what was going on, what would you be able to do? Let me give you a hint. So we were just discussing about this idea of what attention does. What this cross attention does is really it's just figuring out for a given 3D coordinate or for a given ray, what tokens should I look at in order to render my color, right? So if I now asked you to figure out what this thing is doing, what might you look at? Yes? Right. So you could, of course, just look at the attention map, right? You could say, okay, now here's a ray. I'm just going to ask, which tokens contribute to the color of this ray in form of the attention map. Does that make sense to everyone? Okay, good. What would you expect to see? So if imagine I gave you gave you two images, image 1, image 2, and like these are the tokens basically. And you know the camera poses, great. And now, I don't know, well, okay, in 2D it doesn't make any sense. Imagine, I'm just visualizing it. You have to imagine the third dimension, unfortunately. Now imagine you're rendering this ray. So this is the ray we're rendering. What are we doing? We're taking this point and we're taking this direction, and then we're doing, we had this transformer that took all these tokens, just did a bunch of attention, so now these are all the tokens we have. And now we're doing attention over these tokens, right? So, yeah, in 2D it doesn't make any sense. What would you expect in 3D to see in 3D? Like if you looked at the attention map, what would you expect to see? If you like render a ray, what would you expect? Which token would it look at? If you render the ray, which token would you expect the attention map to look at in the two input images? After it's trained, right? Yeah?
Probably whichever the two images.
Right. So what you would expect, right, is if your 3D scene happened to be a 3D scene like this, like let's say that was your 3D scene, we already know you can render the 3D scene, right? That's what we just saw. This thing can clearly render the 3D scene correctly. So for this ray, if you did your geometry right, then you would know, okay, this ray intersects the sphere at this location, and then where would you expect, hence, where would you expect this ray to do, what would you expect the attention map to look like? What you would expect is that, projections, I don't know, like let's say these were the two projections. What you would expect is that the attention map will look something like this. Does that make sense? And in fact, that's what you see. That's in fact what's going on. Okay, so isn't that magical? So, yes?
Does the attention map also notice background, foreground stuff? Like your background is one color with several tokens you activated and not
Yeah. It gets, for these kind of background things, it gets a little bit fishy. Yeah, we don't really know. Well, at least I don't right now know. You could easily check if you wanted to. But for the foreground things, this is exactly what you're seeing. And now let's appreciate for a moment how incredibly cool this is, right? Like, I mean, it's really weird. So what is this thing doing? This thing is doing, without giving it any information about 3D geometry whatsoever, right? This thing is basically figuring out from the images what is the 3D scene. And then when you query it with a ray, it basically learns to intersect the ray with the 3D geometry that it just reconstructed. And then it uses that intersection to figure out which tokens to look at, basically, right? And it does do that, kind of. So that's really weird. And you could imagine something similar might be going on in language. The difference is just in language, even if I, well, I guess I'm sure people are looking at this. Actually, I know people are looking at this. In language, right, what would you do to do a similar analysis to this? You would basically build sequences in made-up languages where you know the grammar exactly, where you know exactly what the rules are for your language, right? And then you would try to see what if the transformer learns these rules in a similar way. And the answer would similarly be yes, it would. And now the big question is why? Why does it do that? Don't know yet. Ask me again in a year. But then I think we'll know soon. Any other questions? Yes?
Actually, the results that you showed for
Yeah.
Is it learning dynamics in bottom left one?
Great question. So what is going on in this bottom left image? So as you can see, this car is driving around. So what do you think what would you expect to see in the input images? In the input images, right, probably the car was moving. So the car wasn't being static while these images were captured. So now what do you see is the transformer doing? And maybe you can figure out why it's doing that as well. So the way this is set up right now is it's assuming that the scene remains static during the time because the time is not an input, so that the transformer can't generate the scene at different time steps. It can just it just gives you one set of tokens, and that set of tokens is constant over time. And so what the transformer does here is it learns correctly, I should say, to blur over the trajectory that the car took, because of course in intermediate time steps the transformer didn't exactly know where the car was, so it just blurs it over. So this is the best it can do in a least square sense. And so that isn't indeed exactly what it does. So yeah, in this case, one way to look at this is kind of that it just has learned to do frame interpolation in 3D, which is, yeah.
Yeah, I mean, I guess it's not just a blur over the whole thing, because it learned to couple it to the direction. I guess if you had a bunch of images from the same camera pose and there was motion, then
Yeah.
but here the camera was moving, so I kind of thought there was some learned some. Yeah, that just coupled the view direction.
Yeah.
It's not actually that blurry.
Yeah. Good point. Yeah, you're exactly right. So basically, one other way of describing this is that this thing has just learned to discover correlations across its input data, right? Like in this case, in the data distribution, in the training data, the input pose was clearly, whenever the input pose moved and there was a moving object, then the pose of the moving camera was correlated with the moving object, which makes sense, right? Because how is this data set captured? This data set is captured with like a car with a 360 camera, right? So if the car is moving, then you have a prior belief over how fast the car is moving, and then you observe that the other car has moved as well. So you can kind of figure out like a kind of approximate rule that says, okay, this is how where I expected this car to be in the intermediate frames, and that's kind of the rule that it has discovered as well. I should say that this result has been improved upon by now, quite significantly, but still not. We're still far away from like photorealistic novel view synthesis. But like maybe in next lecture next lecture I'll show you something there. But like, so this is not yet photorealistic, so this is like not yet competitive with some of the other methods we were discussing, and this is very far away from this like overfitting regime, but we're getting there. Okay, let's move on. Let's get this. Okay, So this concept that we just talked about applies to light fields, the way we were just talking about it, but it's actually a much more general concept. Like, imagine about like the idea that I introduced here was transformers are just a way of learning these kernels, right? They're just a way of learning how should I interpolate a set of values in order to generate a value at a certain coordinate, right? And it turns out that this is a much more general concept. Let me give an example. Last lecture, we talked about this case. Imagine you want to reconstruct a 3D grid of like a 3D grid from a single image, right? And we discussed a way of doing that. And the way we discussed was like you do this thing here, right? Do you remember this unprojection thing? Yeah, you take the image, you shoot rays to each pixel, and then you just copy the value of the pixel into every voxel that it touches, right? Make sense? Do you remember that? And then you could reconstruct a 3D voxel grid from a single image, right? Like this thing. I showed you this thing. Yeah, makes sense? Good. Good. So now let me ask you a slightly funny question. So here's a triplane, right? Do you remember the scene representation? Like this way of parameterizing 3D scenes? Yeah? Okay, good. So now what if I ask you to reconstruct this triplane from the single image? How would you go about doing that? So you might be compelled to do the same thing that we just did with voxel grids. You might be compelled to say, okay, let's think about locally what is the, like, which of these values on this triplane are connected to which pixel, right? That's the way you might think about it. So let's try imagining this, right? So you have these 3 planes floating in space, and now you say, okay, I'm just going to shoot a ray through my pixel, and now what do you do? The problem is that you can't just do the thing that you did with the voxel grid, which is you copied the feature at the pixel coordinate into every value in the voxel grid, into every voxel that it touches. You can't do that anymore, because now this triplane kind of weirdly factorizes the space, right? It basically says, well, for this 3D coordinate, I actually have to generate these three features. And like you could come up with like some weird encoder that tries to do that, but it's very hard. Here's a paper that is 2 weeks old. This is submitted to iClear 2024. This is an anonymous submission. We don't know who wrote it. But the paper is called Large Reconstruction Model for Single Image to 3D. This is trained on a synthetic dataset Observerse. This is, we have the paper. You can go read it. But this paper is literally 2 weeks old. Okay, cool. So we're discussing papers that are from 2 weeks ago. Let's break this apart because it looks very complicated, but you're going to see it's actually exactly what we've been talking about all along. So let's look at this first part. So there's like some weird terminology here, but you can kind of maybe appreciate what's going on. You take a single input image, right? Okay, they encode it into a convnet, and actually all this is saying is just vision transformer. Like split the image into patches and do a vision transformer, you get a token for each patch, right? And like they have like some words, they use a pre-trained encoder from like Dino and whatnot, but doesn't matter. Just imagine here, insert vision transformer. In fact, it would also work with a convnet. It's not really important what the encoder is in this case, okay? Just imagine you take the input image, you stick it through an encoder, and now you split it into patches, and for each patch of the image, you have a token. Like, right? Make sense? Good. Okay, so now you want to reconstruct a triplane from this image. You want to ask, what is the triplane that encodes the 3D scene? But triplane, the geometry is kind of weird. So what you're going to do? you're going to take, so this is in fact a triplane that is like flattened. So this is 3 times 32 times 32, which means there's 3 planes, 1, 2, 3. Each of them has a resolution of 32 by 32. So this is just 3 times 32, okay, it makes sense. And now what are they doing? They're just saying, okay, these are just, this is for each patch on the triplane, for each feature on each of the 3 planes, we're just going to have one learnable token, which is just a free variable. And now, in order to reconstruct the triplane from these image features, we're just going to take each of these tokens and we're going to do cross-attention over the output of the image encoder. So, let me visualize this in 2D. It's maybe easier to understand. Like literally, what you're doing is you're. Is this easy to visualize in 2D? Kind of. Okay. So imagine you have our input image. Beautiful. And now let's imagine we wanted to reconstruct a single token that represented this car, like a single feature vector that represented the whole car. Basically, what they're doing is they're saying, okay, we encode this image with like a neural network into like a set of tokens. I don't know. We split it into these. We put it through a CNN. We split it into these patches. Done. And now what we're going to do is we're going to have this token Z0. It's learned. It's a free parameter of your neural network. You just like optimize this structure. And now what you're going to do is you're just going to do, in order to figure out what the value of this token should be, you're going to just do cross-attention over all of these tokens that are the output of the image encoder. And you're just going to do that once. Okay? And that's what they're doing with this triplane here. They're just taking these 3 planes. They're saying we're just going to flatten them. And then in order to figure out which value to put into each grid element, we're just going to do cross-attention over the output of our image encoder. And why is that reasonable? It's reasonable because now you don't have to figure out what the rule is by which, like what is the local rule by which each value in the grid corresponds to like a value in the image or like to a pixel in the image. That's very complicated. So you just don't do that. You just hand wave it. Yes?
So the position embeddings are the query tokens for the cross-attention?
Yes. Yeah, so learnable positional embeddings. Yeah, I'm realizing we're like, I'm assuming that you're really comfortable with transformers, which I'm not sure if you are all very comfortable with transformers. But like learnable positional encodings is something that happens in transformers a lot. In like Dino VIT, or like in many vision transformers, you have these learnable positional embeddings. Have people heard about learnable positional embeddings before in transformers? No. Unfortunate. Okay. Should I explain it? Okay, good. So, so what is the point of, okay, do people know about positional encodings in language? Like, right? You've seen it in language before, right? Like, it's just this positional encoding is for each token. You're just, imagine you just concatenate like this sine cosine embedding or like something that basically tells you what's the relative position of this token relative to the word that I'm generating right now, right? Okay, so here so sometimes in language transformers, these are not learned. They're just like a function. So for instance, let me give you an example for valid positional encoding. One valid positional encoding might look like this. We have a sentence. What is it? Like the quick brown. Okay, and now we're trying to complete this token. It's clearly Fox, but yeah. Okay, good. So now, like let's imagine we're tokenizing words. So this would be one token, right? This would be one token. This would be one token. And you just look these up in your dictionary of like token, right? And you get like a token for each of them. So far, everyone on board. Okay, good. So now the problem is now we express this token, right, by a cross attention over these. That's how usually it works. Okay. So the problem now is that attention is permutation invariant. So like if you just do cross attention over these tokens, then the transformer doesn't know what the order is of these words, right? It doesn't know which word came first. So what you usually do is you might say, okay, so this is word 0. This is word -1, this is word -2, this is word -3. And now you could imagine that you just, in addition to giving the transformer the token, you also give the transformer the scalar. You just concatenate -3, -2, -1 to the correct word, and then you're just like done. Now you go figure it out. In practice, what they do is they don't actually concatenate like scalars to this, but they do something similar to the sine cosine embedding that we were discussing before. They like have like sines and cosines of these, or like some function. But basically any function that tells you what the order of the words is, right? Okay, good. And now something that you can do alternatively, and I think this is how it's done in like state-of-the-art language models, is instead of like hard coding this, you just say, okay, the word -1, instead of the word at -1, instead of just concatenating is like a hard-coded value, we're just going to learn like a set of values. These are free variables of our model. We're just going to randomly initialize them, and we're just going to concatenate that to our word. And instead of -2, we're going to concatenate a randomly learned vector z1, and so on and so forth. So instead of concatenating -1, -2, -3, you concatenate like some feature vector, some n-dimensional feature vector, and you concatenate a different feature vector for every word, and then you're just learning these as free parameters of your model. Does that make sense? Good. And the same thing is happening here. So for each grid element of our triplane, we're just going to have a randomly initialized vector, which is like a randomly initialized 1024-dimensional vector. And exactly as Cairo just said, this is going to act as the query for our cross-attention. So now for each grid element of our triplane, we're going to take that vector, we're going to do cross-attention over these image features, and that's going to give us the value for that grid element. Does that make sense? Okay, so these are learnable positional embeddings. You see them a lot in VITs and also in language models. Okay, good. And now you have this set of triplane tokens, right? So okay, then they do a bunch of self-attention, whatever. Now you have the set of triplane tokens, right? Again, it's like after this stuff, it's 3 by 32 by 32 times 1042. So for each grid element, we have a 1024-dimensional vector. And now we're just going to reshape it into a triplane. So like we just say, okay, we reshape. And now we can just render it like a NERF. When we want to get a 3D coordinate, when we want to render a 3D coordinate, we take the 3D coordinate, we project it onto the 3 planes. We're going to do bilinear interpolation for each of these planes, which is basically bilinearly interpolating these features here, right, that we just figured out. Stick that, we get like for each of the 3 planes, we get one value. These are these 3 values here. Stick that into our fully connected neural network, and that outputs a density and a color. And now we have basically built an end-to-end model that goes from a single image to a 3D representation, and then we can decode it into a NERF. And then you can train it end-to-end. Does that make sense? I realize this is a kind of, it's kind of a trade-off, right? Okay, so this is obviously like very complicated as a function of the things we've discussed before, but I think it's still worthwhile discussing this because this is giving you an idea of where this stands right now. This paper is something that many people are looking at right now for commercial applications and for all kinds of things, and these are some of the results you can see. So here, take a single image as input, and this is now the neural radiance field that you can reconstruct from the single image. So these are renderings from the neural radiance field. Make sense? Great. Any questions? Yes? Oh, it's anonymous because this paper is under review. So like this is an open review. Like the way the vision and machine learning community works is that there are some conferences like that are hosted on open review. And open review, when you submit a paper, it's publicly accessible, like on arXiv, but the authors are anonymous until the paper gets accepted or rejected. And when the paper gets rejected, the authors can pick to de-anonymize the paper, but they don't have to. But when the paper gets accepted, then the anonymous authors just get updated to the author list. So this is the way we do this is basically the way we do peer review in machine learning. Kind of nice. Yes? It does kind of matter, yeah. But we're gonna skip this. It's a little subtle, I guess. Yeah, we're gonna skip it. Okay. Good, bad, makes sense? Excellent. How much more can I put you through? Gonna skip this. This is probably gonna confuse everyone. Okay, so 20 minutes are an awkward amount of time. Okay, maybe I'm not going to skip this. Okay, we're going to talk about one more type of conditioning just for completeness sake. This is called gradient-based meta-learning. Who has heard about gradient-based meta-learning before? One person. Fantastic. Here's how this works. Imagine we have exactly the same problem as we have before. Like we are in the framework of we want to reconstruct a single object from a single image, right? Make sense? So, and we could do it with this auto-decoding thing, right? Just for the, like light field networks or scene representation networks. So for each object, maybe we have a single latent code, right? And like we say that, okay, good. So here's another thing you can imagine doing. You can say that, imagine that clearly for all of the cars, like let's say I give you a data set of 5,000 cars. Clearly for each of these 5,000 cars, there is a radiance field that parameterizes this car, or light field, it doesn't matter. There's some function that represents that car, right? For instance, there is a function that takes a 3D coordinate and maps it to the color and the density of that car at that 3D coordinate. Cool. So now imagine for a moment that you parameterize that function as a neural network. So for each of the 5,000 cars in your data set, right, now you have one neural network that parameterizes that respective car. Does that make sense? Okay, so the idea of gradient-based meta-learning is to say, imagine that all of these cars are kind of similar, all of these functions are kind of similar, all of these neural networks are kind of similar, in a sense that you can say that all of these neural networks can be derived from one meta-network, which with like one set of weights, and just by fine-tuning that network a tiny bit, you can basically specialize it into any of these like car functions. So this is kind of what you can see here. So you basically say, in this case, these are like some distance function, but it doesn't really matter. So each of these airplanes, for instance, has its own little neural network that parameterizes the geometry, for instance, of that airplane. And now you say, okay, each of these little neural networks are just a specialization of some meta-network. And you assume that you can get the weights of any specialized airplane by a few gradient descent steps on top of that network. That's basically the assumption of gradient-based meta-learning. Okay, and now the key idea of gradient-based meta-learning is that you're going to make that fine-tuning process part of the model. So instead of doing that by yourself, you're going to say, I'm going to build a neural network that I'm basically going to, my only free parameter maybe will be the weights of this meta-network. And now in each forward pass, what I'm going to do is I'm going to take my setups of observations of the airplane, for instance, that I'm interested in. Could be an image, for instance. And now I'm going to just do this thing where I'm going to take this meta network, I'm going to render it, I'm going to compute a loss, and then I'm going to do a gradient descent step. I'm going to do it again, gradient descent step, doing it again, gradient descent step. And it turns out that stuff is differentiable. So the idea is basically you have your meta network, which is basically your neural network, and then you can do like 5 gradient descent steps on top of that neural network. And that now gives you the neural network that represents that object. And now that's what you have your final loss on. But it turns out that the gradient descent steps themselves are also differentiable. So you can basically make this little gradient descent optimization part of the forward pass. So the only free parameters of this whole thing are the initialization. These are the free parameters. So intuitively, what you're saying is, I want to learn an initialization such that in 5 gradient descent steps, I can specialize it to any object that I might be interested in. Does that make sense? Okay. And why this is differentiable is actually there's really no magic here. Like you can literally imagine how this is differentiable. What is gradient descent? Gradient descent is you compute the gradient, which is just a bunch of vector products, right? Like matrix vector product. That gives you the gradient. And then it's like a sum. It's like taking the weights of the network plus step size times these gradients, right? So gradient descent is actually trivially differentiable. You can always backpropagate through gradient descent. There's no magic here. And there is no magic here either. So this is literally just what you do. The only magic maybe is you fix the number of steps. You say we're going to do 5 gradient descent steps at test time. And after these 5 gradient descent steps, we're going to say that is now our specialized network. And that is something you can do. And so like here's maybe another visualization. So you start with your meta network. You do 5 gradient descent steps. That gives you each of your, that gives you specialized networks, right? And at training time, that's literally what you do. At training time, you have your meta network weights. You pick an example from your training set. You do like 5 gradient descent steps on these weights. You get the final thing. And that's what you compute your loss on. And then you just backpropagate it into your meta weights. So this is exactly what you saw here. So here, this is a signed distance function. So we start out with this. This is what the prototype thing looks like. Okay. Oh my god. Oh no, this is annoying. Okay, this is what the prototype. I don't know. So this is what the prototype thing looks like. This is the initialization it has learned. As an initialization, it has just learned this little thing. And now, after 1 gradient descent step, it looks already more like the airplane. After 2 gradient descent steps, it looks more. So in this case, we're fitting a sign distance function. So we have samples of the sign distance function, and we're just fitting the sign distance function. And after 5 gradient descent steps, you can basically get the airplane back. Yes?
So is the in-the-loop specialization, that's also like parameters are fixed, which is the
Yeah, so this was all the hype like some 8 years ago. And this like gradient-based meta-learning has like 15,000 citations. This is what the paper is called, from Chelsea Finch. She's a professor at Stanford now. And there is a million variations on this. But in the first, like usually you make the step sizes also free parameters. So technically, the weights of this network usually are the weights of the network. And then maybe for each step, you have a learned step size, for instance. But now you can make this as crazy as you want, right? For instance, one generalization is you have one step size per step per weight. Like for each parameter in your network, you learn one step size. Or you have a neural network that takes the current thing and predicts the step sizes. Like people have gone absolutely ham with this. In practice, it doesn't do that much. Long story short, this behaves somewhat similar to global conditioning in practice. And what that means is it also doesn't generalize to compositional things in practice. And I think the reason for this, the reasons for this are complicated. We're not going to talk about them. But in practice, you can imagine that this works. This is something you can do, and it will gain relevance again because there is a theory right now that transformers do something like this that is like a lot more sophisticated, but they do kind of something like meta-learning in the loop. This is called in-context learning. So in-context learning is probably related to gradient-based meta-learning, but we don't know yet. But this is worth just imagining. You can read the paper if you want to learn more about it. So keyword gradient-based meta-learning. Okay, any questions on this? I'm not going to quiz you on it, so it's like mostly interesting for posterity. Yes?
So does the hopefully learn one representation for every object?
Yeah, one initialization for every object that exists. And the intuition kind of makes sense, right? Like you say, okay, each chair is kind of similar, and all of the similarities of the chairs, we're encoding it in the weights of like one network. And then the point of the optimization is just kind of to like figure out what particular chair this is. But like all chairs are kind of similar. Yes?
Actually, it's probably very good. I'm thinking about like, do you have some, I guess, one prior, and then you're like fine-tuning it into the optimization. Like this is the optimization process over the weights of the network, but I guess like diffusion is some process over like.
Well, you would be amazed that people have done this with diffusion as well. So like you can imagine that, but we haven't talked about diffusion yet, but you can imagine a thing that you can totally do, which I wouldn't recommend, but you can totally do it. You take your data set and you like, let's say you have your 5,000 airplanes and you fit like one neural network for each 5,000 airplanes. Totally fine. Like now you have represented each airplane with a neural network. And now you can train a diffusion model on top of the weights of your neural network. This is called hyperdiffusion. It's a paper from this year. So like from 4 months ago from like Matthias Nies's group in Munich. Published at NeurIPS. You can do it. It doesn't do anything interesting. It's just kind of, it generates, it's a generative model for little objects. Okay, good. Okay, good. So now we're going to wrap up in a moment, but I'm going to tell you about one more thing. So this is just a refresher. So actually this kind of concludes all of the mechanistic aspects of reconstruction from images. So like we've talked about, what did we talk about, right? We basically said, okay, we want to learn priors over 3D functions, and we've discussed 100 different ways of doing this. You can have this, you can learn a latent space of 3D objects via this global conditioning. You can learn this inference network that goes from images to these latent codes that then allow you to do local conditioning. We talked about transformers. And I hope you kind of got the appreciation of the key ideas, which are basically things like locality. How does locality matter? Quick question. Why does the transformer generalize to compositional scenes? Like this is kind of, and this is maybe something that is maybe clear from the discussion, but like let's just make it explicit one more time. So we said that the key property that allows you to generalize to out of distribution like compositional scenes is this notion of locality, right? We said the property that you have to preserve is from the encoder until the decoder, there always has to be a clear connection between where the input comes from and like how it's related to the thing they're querying, right? How is this true in transformers? And this is maybe another thing to really appreciate for a moment. Yes? Right, exactly. So what's basically happening in the transformer is that you keep this notion of locality. The transformer just learns what locality means, but this notion is still the same. Like, you take the tokens as input, and you don't collapse them to a single token. You keep all of these patches of the images as input, and now you don't hardcode the rule by which the transformer basically interpolates them, but the transformer learns the rule by which to interpolate them. And it turns out that the rule that the transformer learns ends up being the same rules of locality that we discussed before, kind of high level. Make sense? So transformers do work for compositional scenes, and the reason is because what we just said. Okay, good. So we discussed all of this now. And yeah, I think actually now you're kind of up to date with what's going on in this in that part of the research, which is the reconstruction part of research. So, well, like there's obviously much more interesting stuff, but just on the part of like neural network architectures that connect images to 3D scenes, you've basically heard everything now. There's like nothing more going on right now. Every paper that you're going to read at iClear this year or at CVPR this year is going to be a version of this framework that we just discussed about. Like, all of them are going to look like that. All of them are going to take images, split them into, I don't know, CNN, local conditioning, single latent code, transformers, probably lots of transformers. But basically, that's what it's going to look like. In fact, the paper that I just showed you was from iClear. Cool. So, like, now, the last thing that I want to teaser is what have we, like, so far, all of the discussion that we just did, what does all of this allow us to do? All of this allows us to do reconstruction from few observations. That's what it allows us to do. I give you a few images, you do 3D reconstruction. Great. But that's actually not what we set out to do. What we set out to do is not reconstruction. What we set out to do is also reconstruction, but also understanding. The objective was, I don't only want to be able to reconstruct the 3D scene, I also want to understand what each of the objects in the 3D scene is, right? Which is usually the goal of self-supervised learning. And let's think back to our motivation for all of this prior-based inference stuff. Our motivation was these autoencoders, right? And we actually discussed these autoencoders in that same framework. We said, okay, these latent codes that you have learned, what do these latent codes encode? And in the autoencoder, we said, well, it doesn't really work that well, so the idea was basically the same, that you have, like, I don't know, in the latent code, in the latent space, you would hope to find these semantic concepts. In practice, it does work on MNIST. So on MNIST, you can find these semantic concepts, but it doesn't work for anything else with autoencoders, right? Okay. So now, in self-supervised learning, we are kind of, we have talked about all of these reconstruction things, and we have talked a little bit about, like, what these feature spaces allow you to do, right? We talked for a moment about the semantic segmentation stuff, but really, we haven't really investigated these latent spaces yet, like allow you see if they have any semantic meaning. And that's something we're going to discuss next time. So basically, for learning good representations, we don't actually usually care about, like, whether the reconstruction is perfect. What we really care about is, like, whether semantic concepts appear. So, like, I don't maybe care about, like, getting every piece of this car or every piece of this chair exactly right. And in fact, right, you know this very well. When I close my eyes, all of that detail is gone. What do I remember? I remember that there's a chair in front of me, and I remember maybe, okay, the chair had some pattern and so on, and if I was, like, a really gifted artist, I could draw you something that looks kind of like the chair. But all of that fine detail is gone. Like, the thing that you commit to memory is a much more abstract representation than all of this fine grain detail. But all of the stuff we were just discussing is seemingly concerned with only reconstructing all this fine grain detail. And that is apparently kind of a weird mismatch. And there's another little thing that I will maybe give you on the way. So there's this thing that is really a machine learning problem. Like, in machine learning, like in self-supervised learning, what do we assume? In self-supervised learning, we assume that we're learning from raw observations. So, and one way you can learn from raw observations is, for instance, by saying we're going to predict the future. So, like, conditioned on what I'm seeing right now, my brain might be predicting what will happen in the next time step. So my brain might be saying, okay, for instance, when I move my head, this is how this image will change. And that's, maybe by now, you know this is how we learn about 3D, most likely. Like, your brain is basically saying, when I move my head, like, how does the image change? And the way the image changes as a function of how you move your head is 3D. That is exactly what tells you about 3D. But that first order, that seems to mean that the way your brain does this is by predicting what the photorealistic image will look like in the next time step. Because the only thing that your eyes are measuring are photorealistic images, right? So in order for using that as a learning signal, seemingly, your brain must be giving you like some belief over what it looks like photorealistically. So now the question is, does your brain have a photorealistic renderer in it that like reconstructs a 3D scene, and then it does like, and it, in all its detail, and then it reconstructs it, and then it says, okay, when you move your head, I'm going to render it from this angle, and then it's going to, maybe, but maybe not. And this is one of the motivations for contrastive learning, which we're going to talk about next week. So instead of doing learning from reconstruction and just comparing pixels to each other, there's this idea of contrastive learning, which basically says, instead of doing that, what we're going to do is, from an image, we're going to infer some high-level representation. And then what we're going to do is we're not actually going to compare pixels to each other, but we're always going to compare stuff in like some abstract latent space or feature space. And that there is ways of making that work. We haven't seen that much in 3D representation learning yet, but there's enough to talk about. And that's what we're going to talk about next time. Thanks for coming.